Hello everyone. Today we will be discussing the second method of minimization of deterministic finite automata. In the previous slides, we discussed about the first method for minimization of deterministic finite automata. Now we will be discussing the second method, that is what we call as lower triangulation matrix method. Now consider the following DFA. This is the same example which we considered in the previous slides. Say for example, we have this particular DFA. The first step which we need to do is that we need to draw the transition table corresponding to the given DFA. So we have 5 states, A, B, C, D, E. We have one start state A and one final state E. Now what we will do, we will draw a lower triangulation matrix of n minus 1. That means if I have 5 states, I'll draw a lower triangulation matrix of 4 cross 4. Very first step which we need to follow is that we will mark all the rows and columns with final states with 1. Since E is the final state, so we will mark 1 on all the rows of E. Now, second step is we will start the iteration corresponding to every row and every column. We will check what is the value corresponding to the sigma. Here sigma is AB. We will start with AB. Since this is the first cross section of our matrix, AB on A. AB on A gives us BB. That is this point. BB does not exist in the matrix, so we will not make any change in the lower triangulation matrix. Next is AB on CD. If we see AB on CD, CD is unmarked in this matrix, so there will be no change. Next, we go to AC, that is second row, first column. AC on A gives us BB. This is the point which does not exist in the matrix, so no change. Next we will see AC on B. Again we have CC. CC does not exist in the matrix, so no change. Next we move to BC. BC on A goes to BB. Does not exist in the matrix. Then we move to next point, that is BC on B. This gives us CD. This is the point. CD or DC is same. Since CD is not marked as yet, so there will be no change. Move to the next row, first column, that is AD. AD on A gives BB, which does not exist in the matrix, so there is no change. Now we come to AD on B gives us CE. Just see, CE is marked. Since CE is marked, we will mark AD with 1. Next we move to BD, that is third row, second column. We will check BD on A. We get BB, which does not exist. Next we check BD on B. At this point we get DE. Now since DE is marked, we will mark BD with 1. Next we move to third row, second column. This is CD. Now corresponding to CD on sigma equal to A, we get BB, which does not exist, so no change. Corresponding to CD on B, we get CE. CE is marked in the original table, so we will mark CD with 1. Now our first iteration is over. We have checked all the rows and all the columns. Now we need to look at all the blank entries in the second iteration. We are naming it as second iteration because we have covered every row and every column of the matrix, and now we are starting again with the same thing but second time. Now we have 3 entries in this entire matrix which are unmarked. First is AB, second is AC, and third is BC. We will recheck all these entries. So first comes AB. AB on A goes to BB, which does not exist in the matrix. AB on B goes to CD. Now just see, earlier CD was not marked in the first iteration. Now in the second iteration, CD is marked. Since CD is marked, we will mark A. Next we move to next point, that is AC. AC on A go to BB, which does not exist, so no change. Now we move to AC on B, which is CC. CC also does not exist, so this will remain unmarked. Next, in the matrix which is left out is the BC. BC on A is BB, does not exist, but BC on B gives us CD. CD is marked now, so we will mark BC. Now we have only one row and column which is left out. We need to recheck it so that if there is any entry corresponding to the row and column in the second iteration, we need to look through it. Now we will check AC on A. It gives us BB, which does not exist, and we will check AC on B. This gives us CC, which does not exist in the matrix. So now we can conclude that since AC remains unmarked in either of the cases up to third iteration, that means A and C can be merged. That means ultimately we can minimize our original DFA with 5 states to the DFA with 4 states where state A and C have been merged together. So this is how we have minimized our 5-state DFA into 4-state DFA using lower triangulation matrix method. Now we will consider the second example in which we have 8 states ranging from A up to H. First step will be that we will draw the table corresponding to the given DFA. Here we have A as a start state and C as the final state. Now we will draw the lower triangulation matrix. We will have lower triangulation matrix of 7 cross 7 since total number of states were 8, and the matrix which need to be drawn is of number of states minus 1. First step will be that we will mark all the inputs corresponding to final state with 1 in the lower triangulation matrix. We have 2 rows, we have marked them, and we have 5 columns which we have marked. So this is the first step. We need to mark all the rows and columns corresponding to the final state. Next, we will keep on checking each and every crossing. Now the first cross point is AB. So since sigma is AB, we will check AB on A. We go to BG. BG is not marked, so there will not be any change in the lower triangulation matrix. Next, we move to AB on B. This gives us FC. FC is already marked, so we will put 1 in AB. Next, we move to AD. AD on A gives us BC. Since BC is already marked, we will mark AD with 1. Next, we move to BD. BD on A gives us GC. GC is already marked, so we will mark BD with 1. Marking of 1 means that these two states cannot be clubbed together. Now we have AE. AE on A gives us BH. Since BH is not marked, there will be no change in the lower triangulation matrix, no marking. AE on B gives us FF. This FF point does not exist in the matrix, so there is no change. Next, we move to BE. BE on A gives us GH. GH is not marked, so no change. Now we move to BE on B. This gives us CF. Since CF is already marked, we will mark BE with 1. Next, we move to DE. DE on A gives us CH. CH is already marked, so we will mark ED. Likewise, we move to FA. FA on A gives us BC. BC is already marked, so we will mark FA. We move to FB. FB on A gives us GC. GC is already marked, so we will put a 1 in BF. Next, we move to DF. DF on A gives us CC. CC does not exist, so there will be no change. Next, we go to DF on B. This gives us GG. GG does not exist, so this particular cross point, that is, this will remain unmarked. Next, we move to Fe. Fe on A gives us CH. Since CH is already marked, we will mark this. Next, we move to AG. AG on A gives us BG. BG is not marked as yet. So we will check this corresponding to B. AG on B gives us FE. FE is already marked. So we will mark AG with 1. Next, we move to BG. Corresponding to BG, we get GG. GG does not exist, so no change in the matrix. Corresponding to BG, we will check whether there is any input on B which can be marked. Yes, we get CE. CE is marked, so we will mark BG also with 1. Next, we move to DG. Corresponding to DG, on A, we get CG, which is already marked, so mark it. Move to GE corresponding to A, give us HG, not marked. GE corresponding to B gives us FE, already marked, mark it. Next, we move to FG. FG on A, CG is already marked, mark this. Now we move to the last row, that is of H. HA corresponding to HA, BG. BG is already marked, so mark this. Move to HB. HB on A gives GG, does not exist. Check on B. HG on B gives us CC, does not exist. Move to HD. HD on A gives us CG, already marked, mark it. Next we move to HE. HE on A gives us HG, which is not marked, so we will not mark it. Move to HE on B, we see it is FC. FC is marked, so this is marked. Next we move to HF. HF on A gives us CG, which is already marked, so we will mark this. And then the final one in the first iteration is HG. HG on A gives us GG. GG does not exist. And HG on B gives us EC. EC is already marked, so we will mark it. So with this, we complete the first iteration of the matrix. We have scanned every row and every column of the matrix. Now we have 3 entries which are left out. One is AE, second is BH, and third is DF. So in the second iteration, we will look towards these 3 entries in order to identify whether there is any input corresponding to these. The first one which we are considering is AE. AE on A gives us BH, which is as yet not marked. Now we move to FF, does not exist, so AE remains unmarked. Then we move to the next input which was unmarked, that is BH. BH on A gives GG, which does not exist, so no change. BH on B gives us CC, which does not exist, so no change. That means BH remains unmarked. Third one which was left out is DF. DF on ACC does not exist, no change. DF on B gives us GG, which does not exist. So ultimately, from these particular inputs, we can easily identify that there are 3 states which can be merged. State A can be merged with state E, state B can be merged with state H, and state D can be merged with state F. So we get 5-state DFA in the end. AE has been merged, BH has been merged, and DF has been merged as a single state. So this is the final output after the minimization of this DFA. That is, 8-state DFA has been minimized to 5-state DFA. So we have discussed the minimization of DFA. That means we have identified whether there is any redundant state, and if there is, we have removed it. In the first example, we had 1 redundant state. In the second example, we had 3 redundant states. One method was discussed in previous slides, and one method has been discussed here, and questions have been solved using both these methods. In the coming slides, we will be discussing how regular expression can be generated from the given DFA. Thanks.